Which quantity is largest? The number of stars in the universe? The number of water molecules in Earth's oceans? The number of orderings of a 52-card deck? The number of grains of sand on Earth's surface? Or the number of seconds since the beginning of time? Let's explore this mystery by studying mathematical objects called permutations. We start our play with a set of 6 colored balls, and we wonder, how many ways can we put these balls into a specific order? We'll find it helpful to label the balls with the integers 1, 2, 3, 4, 5, and 6. To determine an order for these balls, we create one bin for each ball. Again, we label each bin with the numbers 1 to 6. Now, let's look at some ways to order these balls. We could leave the order of the balls unchanged by simply maintaining the natural numerical ordering on these balls. This corresponds to doing no work, which is my favorite amount of work to do. Another option is to make swaps in pairs of 2, without thinking too hard about how to do this. Yet a third way to do this is to push and pop. Push each ball one to the right and pop the last ball back to the start. For a fourth choice, we could get our fancy pants on and do something much more interesting that I will not try to say in words. After about 15 seconds of play, we've created 4 different examples. If we keep going in this fashion, we might wonder, how many different orderings of n balls are there? What patterns do we see in this setup? How is this related to our lived experiences? Let's set up 4 rules to help us define what are permutations. Our first rule for permutations is that the number of balls must equal the number of bins. In our previous examples, we had 6 balls and 6 bins. This satisfies rule 1. Of course, we can imagine different problems, like what happens if we have more balls than bins, or if we have more bins than balls. Ain't nobody got time for that, at least not in this video. These situations violate rule 1 and thus are not part of our study of permutations. Rule 2 for permutations is that the n balls and n bins must each be labeled with the first n positive integers. To study permutations using 8 balls and 8 bins, we gotta label all balls and bins with distinct integers, just like we see here. If we set up a sorting process where some of the balls are labeled with the same number, we violate rule 2. Similarly, if we label some of the bins with the same numbers, we do not pass go and we do not collect $200. Our third rule for permutations is that we must assign all balls to a bin. In our push and pop example 3, we did assign all balls into a bin, which satisfies rule 3. Imagine, however, that we determine an order for the balls by placing them into bins and we leave some balls unassigned. You didn't say the magic word. This violates rule 3 and the resulting map is not called a permutation. Our fourth and final rule for permutation play is that each ball can only be placed into a single bin. In example 1D, we follow this rule so that each ball is in a monogamous relationship with a corresponding bin. We violate this rule if at least one of our balls is 2-timing and gets assigned to more than one bin. Now that we know some rules for our game, let's explore how we can describe permutations. Think back to example 1A. To describe this action, we can use function notation. Let's name this permutation using the Greek letter pi. We'll think about each ball as a unique input value and the bins as the corresponding output values. When we place ball 1 into bin 1, we write that pi of 1 equals 1. The value inside the parentheses is called the input, and the value on the right-hand side of the equal sign is called the corresponding output. We can write the same relationship in arrow notation by saying that pi maps input value 1 to output value 1. Similarly, when we place ball 2 into bin 2, we write that pi of 2 equals 2. We continue like this until we have a complete list of input-output relations that follow our 4 rules for play with permutations. Permutations are often named using Greek letters. For example 1A, we named our permutation with the Greek letter pi. We could have also used the letter sigma, or tau, or perhaps alpha, or beta. Beyond the permutation name, it can also be helpful to label permutation using subscripts. For example, we might tag a permutation name with a subscript, like a positive integer, so that we can distinguish between different permutations that are labeled with the same Greek letter. For this example 1A, both function and arrow notation lead to a long list of symbols that we need to record to fully describe our permutations. Imagine having to write all this out by hand. Ugh, How tedious, right? You know what sound mathematicians make when we have to do tedious writing labor? Yeah, that's right. Construction workers protect themselves against nail gun injuries, and mathematicians cry about overly demanding notation. This is a first world problem, but the struggle to create good notation in mathematics is often worth the effort. So let's think about how we can turn our suffering into inspiration. Specifically, what if we created a special permutation diagram to make this easier for ourselves? We start with the inputs and create a dot representing each ball, labeled with the positive integers. Then we move to the outputs and create another dot directly under the inputs and similarly labeled. And we notice that input value 1 is mapped to output value 1. Thus, we draw a line from input dot 1 to output dot 1 in our permutation diagram. We repeat this process for input value 2 by drawing a line to its corresponding output. We move on to input dot 3 and connect that to output dot 3 for this example. We complete our permutation diagram by connecting all input dots to the corresponding output dots. But that's not all we can do. We might be more efficient by reducing this diagram down to a two-line notation. In two-line notation, we create a two-row n-column matrix using large parenthesis symbols. In this case, n equals 6 since we have 6 balls. In the first row of our matrix, we write the input values, which are the numerical labels for each ball. Directly under input 1, we write the corresponding output value, the bin number, where input 1 is mapped to. Next, we move to input 2 and write the corresponding output in the appropriate place. We continue in this manner until we have fully defined the input-output relations for the entire permutation pi1. This two-line notation is quite compact and saves our hands from carpal tunnel syndrome. Because notation matters, let's get some more practice using example 1b. In this case, we place ball 1 into bin 2. If we name this permutation pi2, then we say pi2 of 1 equals 2. We can also draw our permutation diagram and connect input dot 1 to output dot 2 for this action. Next, we place ball 2 into bin 1 and we say pi2 of 2 equals 1. In our permutation diagram, we connect input dot 2 to output dot 1. Since ball 3 gets placed into bin 4, we write that pi2 of 3 equals 4, and we connect input dot 3 to output dot 4 in our diagram. We do this dance on and on and on till the break of dawn so that we fully define our entire permutation pi2.